electric field over each face of the box, 15, 20, 15, and so on. Those are all in newtons per coulomb. We also see that each of these arrows shows the direction. So for this one, the electric field points in toward the box. For this one, the electric field points away from the box. So we know the direction and we know the strength. It says that the electric field is constant for every face, and we want to know the sign of the charge inside the box. We can figure this out using Gauss's law. So Gauss's law states that the net electric flux through a Gaussian surface, our Gaussian surface in this case is the box, is equal to the integral of E dot dA equals the charge inside the box divided by the constant epsilon naught. So if we can sort out what is the sign of E dot dA, it'll tell us what is the sign of Q enclosed. So let's figure out this integral side first before we start to decide what to do. So the integral of E dot dA is equal to, it says here that the electric field is constant over every face of the box, so the electric field can come outside the integral. So we have E dotted with the integral of dA. The integral of dA is just the area A. So the integral of E dot dA is the same as E dotted with A. E dotted with A is the scalar product between the electric field and the area, so that's going to be E times A times cosine theta. And as a reminder, theta is the angle between the electric field vector and the area vector. So to carry on, the next thing we need to sort out is what do we mean by the area vector. So if we have a surface, the area vector is defined as being perpendicular to the surface and facing out of the surface. So that's the definition of an area vector. So if we had a cube like this, the area vector, I'll try and draw them on every face. On the top it points up, the bottom it points down, the front it points out, the back it points out, this side out, and on this side also out. There, I think I got every face. So the area vector points outwards everywhere. So what we'll have to do is figure out what's the direction of the area vector, what's the direction of the electric field vector, find the theta, and it'll give us something about this side of the equation. Okay, so let's do E dot dA for every face of that box. So we'll do the top face first. So this is going to be equal to. So for the top face, the 15 points down, the area vector points out. So let's draw that right on this picture. The area vector points out. So there's our area. So the angle between these two guys, this one's down, this one's up, the angle between those two is 180 degrees, and cosine of 180 is equal to -1. So for our top face, we have 15 times the area times cosine of 180, which is -1. So this is the top face. On the top, theta equals 180 degrees, cosine theta equals -1. Okay, that's for the top face. Let's do the side face next. So we have our electric field, 15, times our area. For this guy, the electric field vector is out, the area vector is out. So for this one, that angle is 0, and the cosine of 0 is equal to +1. So this is for the right face. For this guy, theta equals 0, and cosine theta equals +1. Then we'll do the next face. Let's go to the bottom next. So on the bottom face, the area vector comes straight down like this. Those are opposite in direction. That angle is 180. So for this guy, we have plus the electric field of 20 times the area times the cosine of 180, which is -1. There's the bottom face. Next, we'll do the front face. The electric field is 15. It points inwards. Our area vector points outwards, so that angle is 180. So for our front face, we have 15 times the area times cosine of 180, which is -1. Then we'll do the left face. So So our 10, our electric field points out, our area vector points out, so the angle between those two guys is 0. Cosine of 0 is 1, so there's this face. Now let's see, what do we have left? Got the back face left. So our electric field points out, our area vector also points out, the angle between those two guys is 0, and the cosine of 0 is 1. So our last face is plus the electric field, which is 20, times the area, times cosine of 0, which is 1. So that's giving us the total for our integral of E dot dA for every face of that box. So let's look at what we have here. So this is minus 15 times A, plus 15 times A, minus 20 times A, minus 15 times A, plus 10 times A, plus 20 times A. Some pretty simple algebra here. Minus 15 plus 15 is 0, minus 20 plus 20 is 0, minus 15 plus 10 is minus 5. Minus 5 times the area, and that 5 has units of newtons per coulomb. So let's put this result in up here. Minus 5, why don't we just go ahead and put the units on there, newtons per coulomb times the area of any single face of the box equals Q inside over epsilon naught. We're asking about the charge. We don't really need to solve for this, but let's do it anyway. Q inside equals minus 5 newtons per coulomb times the area of the face times our constant epsilon naught. If we knew the area of the face, we could go ahead and calculate Q inside. We're only asked for the sign. We see here that that sign is negative. So the net flux is negative, which means that the charge inside the box is negative. So the answer to our question is B, negative charge. Okay, and then next we'll go on to this problem.